Welcome to the second video of my 10-part lecture series on calculus. Today we will be covering Chapter 2, dealing with limits and continuity, from the textbook Calculus, Graphical, Numerical, and Algebraic, 3rd edition. The sections we're going to be talking about today are rates of change and limits, limits involving infinity, continuity, and finally rates of change and tangent lines. So 4 sections in total today. Now the first section we're going to be covering deals with rates of change and limits. This will be divided into 4 subsections: definition of limits, properties of limits, one-sided and two-sided limits, and the sandwich theorem. So let's dive right into it. Definition of a limit. So let's take a look at this graph below. One moment. So right here we have what looks like a smooth curve. Now right here it says the definition of a limit. Assume f is defined in a neighborhood of c and let c and L be real numbers. So right here we have an x value of c and we have a y value of L. The function f has limit L as x approaches c. If, given any positive number e, there is a positive number delta such that for all x the following here is true. And I'm not going to read all that out. But what is this saying? This seems like a very confusing wording for something that's actually relatively simple. Well, it's saying here that as we approach a certain value of c on the x-axis, we're approaching another certain value of L on the y-axis. And you might be asking yourself right now, well, if we want to find out what L is, why don't we just plug in c for x into our original equation? Let's just say that this is f of x right here, function f of x. Why don't we just plug in value c into our original equation so that we can finally get our y value, which we're for some reason calling L here? Well, in this situation where we have a smooth curve, that's totally possible. We could simply figure out the limit or what value L is here by plugging in c into our original equation. However, as we will soon find out, not all functions look like this. Not all functions look smooth like this. In fact, let's just say that at point x equals c, we had something called a discontinuity, a break in the function. Well then, where the original function would not be defined. Well, what do we do in that scenario? Well, we want to know the limit. The limit as x approaches c is going to be how close we can possibly get to this point without touching it, and what that number would look like. Let's go on to the next slide here. So let's take a look at these 3 graphs right here. We have f of x equals x squared minus 1 over x minus 1. Well, if you notice, at a certain point here, there is a little hole. So if we try to plug in the number 1 for x into our original equation, we'd be dividing by 0 here. And if we divide by 0, of course, then our graph would be undefined, which it is right here. Well, so if we wanted to know, we don't have a y value at x equals 1. The closest thing we can do is to find the limit. So we can see how close, as we get closer and closer to x equals 1, what is our y value limiting to? What number are we ultimately approaching? And it looks like 2. So if I approach this value right here as closely as I can without actually touching it, we're going to get ever more closely to the number 2, which means that the limit of this function at x equals 1 is going to be equal to 2. This is called a discontinuity, by the way. Right over here, we have a different scenario. We have a scenario, well, it's very similar, but a different scenario where the function at x equals 1 actually is defined. So if we plug in x equals 1 into g of x over here, then we get a value of 1. But does this really look like the behavior of the rest of the line? It doesn't. So that's a problem. Well, how do we resolve this problem? We can make a distinction. We can say that the limit as x approaches 1, the limit of y is 2, right? Because we get ever closer to this point right here, y equals 2. However, we never reach it. And at the actual value, x equals 1, we already know that y equals 1. So let's go on to our third graph. Here's a situation where we could just plug in x equals 1 into our equation, and we would get a y value of 2. And the limit as we approach x equals 1 is also 2. So in all three cases here, the limit as x goes to 1, so as we get closer to 1 on the x-axis, the limit that we're approaching is y equals 2. However, for each individual function, we have a different actual value if we plug in x equals 1. For this one right here, we have an undefined value. There's no y value for when x equals 1. For this function right here, we do have a value. We have x equals 1, y equals 1, but it doesn't really match with the rest of the graph here. And finally, in function c, right here, h of x is equal to x plus 1, we just have a straight line where the limit and the actual value, the limit as x approaches 1 and the actual value where x equals 1 is the same. But that's not always the case, as we can see in the first two graphs. So let's look a little bit at how limits, at the notation of limits. We have this right here. We have limit of x as it approaches 1 of f of x equals 2. This is true for all three of these graphs here. And let's break down each component of this notation. So first of all, if we see this right here, lim lets us know that we are looking for a limit value and not a function value. Okay, so let me repeat that. Lim lets us know we are looking for a limit value and not a function value. So in all three cases here, we're looking for the limit as x goes to 1 of each of these three functions, which happens to be number 2, y equals 2 for all three of them. This bottom portion here tells us that the name of our variable and what value it's approaching. So here we see x as it approaches 1. So that means that from both the left-hand side, as we approach x, as we get ever closer to it, it's approaching 1. This portion, of course, tells us the name of the function we're working with. So the first function here's name is f of x, g of x, h of x. But just know that if this was f of x, g of x, h of x in this situation, the limit would be the same. So we just put the function name of the function that we want to take the limit of and what x value we are approaching. And then finally here on the right hand side of the equation, we have the y value that we are approaching as we head to this x value. So as x goes to 1, y is going to get ever closer to the value 2, but it might not necessarily ever reach it. Okay, well, if we were just plugging in values for x, I mean, that would be easy, right? But when we're dealing with limits, we have a few rules that we have to deal with. We have the sum rule, the difference rule, the product rule, the constant multiple rule, the quotient rule, and the power rule. And we'll go into that in more depth a little bit later. So let's look at an example. So we have a certain function here, 4x squared divided by 1 plus square root of x. And we want to know what the limit is. Now, if we wanted to know what the y value of this function here was at x equals 9, we could simply just plug in 9 for x to give us our ending value, our ending y value. However, we have to use a slightly different notation here when we're dealing with limits. So let's take a look. So we have limit of x as it approaches 9 of 4x squared divided by 1 plus square root of x. First, we're going to apply what's called the quotient rule, meaning that if we have a limit of this entire function, we can split the limit up into two and take the limit of the numerator as well as the limit of the denominator independently. That's called the quotient rule. And here we have what's called the constant multiple rule, where if you have a variable such as x that has a constant out in front of it, you can move the limit notation inside. So you can just keep the 4 on the outside here and not have to deal with it. So limit of x as it approaches 9 of x squared. We can just pull this 4 out in front, and that's known as the constant multiple rule. And right here we have the sum rule for the denominator. So we can distribute this limit through to 1 and through to square root of x to take the limit of each of these components here individually. And so once we get to this stage, what we can finally do is we can actually just plug in 9 for x into each of these different values. Now, if we have a limit as x approaches the 9 of x squared or x, then we can simply plug in 9 into x. And also right here in the denominator, if we take the limit of x as it approaches 9 of a constant, then that constant is just going to remain the same. So what happens when we plug in 9 for all of these values? We get the answer 81. We plugged in our values here at the end to find the limit of our function as x approaches 9 to be 81. Now these limits, they have different sort of properties and different theorems. We have the polynomial and rational functions limit, and what this is basically saying is that if we have rational and polynomial functions such as these ones, there is the limit as x approaches c is simply what happens when we plug in that c value for x and whatever happens to the y value. Now, certain functions have one-sided limits and certain functions have two-sided limits. And we're going to learn a little bit more about that. So right over here, we have an interesting looking graph here. As you can see, we have several jumps here in the graph where we have holes in it, and these are called discontinuities because the graph is not actually continuous at these points. It looks like at x is equal to 1, x is equal to 2, x is equal to 3. It's not smooth. And it also looks like we have different limits when we approach the graph from different sides. So we have, well, let's take for example this limit right here. As x approaches 1, what is our limit? Is it y equals 1 or y equals 0? Well, that all depends on which side you are approaching x equals 1 from. If I approach x equals 1 from the left-hand side, then the limit appears to be 0. If I approach x equals 1 from the right-hand side, then the limit appears to be 1. And so this graph has both both right-handed and left-handed limits. So let's take a look at this notation here on the right-hand side. So if you have a plus sign here, the plus sign tells us that we are approaching the limit from the left. So we would use this notation to describe what's going on at x equals 1 if we were approaching it from the left-hand side. So if we're getting ever closer to x equals 1 from the left-hand side, the limit would pretty obviously be 0. And we can see that over here. So if you see this notation plus, you know that your x value has to be increasing, you have to be approaching from the left. And that's known as a right-hand limit, so it's the opposite. So left-handed limits are the exact inverse of that. The minus sign tells us that we are approaching x equals 1 from the right. So take a look here. as we approach x equals 1 from the right, our limit appears to be y equals 1. So remember, it's flipped. So if you have a plus sign, it's called a right-handed limit, but you are approaching that x value from the left. If you have a minus sign, you are approaching the limit from the right-hand side, but it's called a left-handed limit. I know it's a little bit confusing, but it's just something you're going to have to memorize. So let's go to the next slide here. The next theorem for limits that we have is called the sandwich theorem, and it states that if we have a function g of x and a function h of x, and another function sandwiched in between them called f of x, and both of these outside functions are continuous, then the inside function must be continuous too at a certain point. So let's see what that actually graphically looks like. And remember, so h and g on this graph are continuous. That means that there are no jump discontinuities, no discontinuities of any kind. So this graph has a ton of discontinuities here, and discontinuity means the points where it is not smooth. So take a look at these different points here. However, this graph right here, all three of these functions don't look like that. They're all very smooth, and this theorem simply states, the sandwich theorem simply states that if you have a function h of x and g of x, and they both have the same limit at a certain point, and then you have an f of x function sandwiched in between them, which you would know if the y value at that point is takes this form where g of x is less than f of x and f of x is less than h of x, then the limit at that point has to also be the same as for these first two functions. So if the limit of g of x at the point at x equals c is the same as the limit of h of x at this point x equals c, then and f of x is sandwiched in between these two functions, that means that f of x also has to have a limit at x equals c.